Today is going to be a presentation of another lecture on our inorganic chemistry. Don't forget we have started with metals and their compounds. That is two lectures ago, and lectures last week we went further in discussing the properties and some preparations on some few compounds of some representative elements like sodium, like magnesium, like aluminium. Today we are going to move forward, and it's going to be on metalloids. Active side 80%. At the end of today's class, it is expected that we should be able to describe the general properties and preparation of some metalloid, even some of their uses, and in particular we will go forward to describe the preparation of some compounds of boron and silicon as the representative elements of the metalloids we are going to take today. So we are familiar with this periodic table, and we are made to realize that the left side here is for the metals. We have the far right here for the non-metals, and in between them, like this, up to this place, like this, is for the metalloids. So we want to take this metalloid today, and especially in detail we want to take boron and silicon, because those are the most common elements, and their compounds are the most common in metalloids. So these are the boron and silicon that we want to take for today. So as a matter of introduction, metalloid are composed of 6 elements of the periodic table. So those elements separate the metals from the non-metals. So these are boron, silicon, germanium, arsenic, antimony, and tellurium, as I have shown it to us on that periodic table. So those elements, they look, and in appearance they look like metal. That is, they shine, they are luster, they sometimes they have good well arranged crystal structure. They are luster, they shine when you look at them, especially boron and silicon. But the only thing is they have mobile electrons also, but the electrons are not able to conduct electricity like the way metals conduct electricity. So in such a way they are not metals in actual sense, but they are better than non-metals in terms of electricity conduction. So they are like semi-metals. So their chemical behavior falls between that of metals and non-metal. So in the case where they look like a metal, is because they do not form anions. Like metals do not form anions, they do not form anions also. And again, they have covalent bond like non-metals. So they have, in some aspect, they have properties of non-metal. In another aspect, they have properties of metal. So their chemical behaviors are somewhere sandwiched in between the properties of metals and non-metals. That is why they are called metalloid or semi-metals or semiconductors, as the case may be. So let's try to look at all those elements in that group. So boron, we said boron exhibits some similarities to carbon and silicon, because carbon is a direct neighbor of boron. Boron belongs to group 4, group 3, carbon belongs to group 4. So silicon is also like that. If you look at this periodic table now, this is boron, that is group 3, this is carbon, group 4. So carbon and silicon are of the same group. So boron has some similarities that are similar to carbon, and some similarities that are similar to silicon, because they are in the same family as metalloid. So all 3 elements form covalent compound. That is, the common properties that is common to the three of them. Not only the three of them, all those elements that we are going to talk about today. The electronic structure of boron is 2s2 2p1, as we have discussed during our subject on electrolysis. Boron has 5 electrons, so the first 2 occupied by the first shell, then the last 3 by the last shell. The last shell. So it has oxidation number of +3 because of these 3 electrons in the outermost shell in the compounds, but can also form fractional oxidation state because of the imbalance between the valence orbitals and the valence electrons. So there is imbalance, so that gives it extra instability, which can make it to form various it can react with non-metals in various ways. So example is in boron hydride, where the number of hydrogen atom present can dictate the oxidation number of boron. So in the case where we have 4 hydrogen atom, we can have 12. So in that case, we can have either we have fractional oxidation state, or we have odd number oxidation state. So it is only boron that can exercise this out of the metalloids. On the other hand, silicon has a valential electron of 4, so it forms that tetrahedral structure convertibly. Boron form trigonal because of the 3 elements in the atmosphere, but silicon form tetrahedral shape like carbon. It forms a tetrahedral, and it's because of the hybridization in sp3 orbitals. We are going to talk more about hybridization when we get forward in this course. So the oxidation number of silicon is usually +4 because of the 4 electrons in the atmosphere. So let's go to the lower members, the arsenic, the antimony, and tellurium. So they form compound with oxidation number of +3 and +4. So we don't need to know much about arsenic, antimony, and tellurium. Just get some of these properties and just go. So our interest is basically on boron and silicon. So if we look at them structurally now, we want to compare these elements together with graphite. We said they have some striking similarities, but some properties are also different, differentiate them. So covalent bonding is the key to the crystal structure of the metalloids. So they have covalent bond, so they are similar to carbon, because carbon is also a non-metal that has covalent bond. So in this case, these elements resemble non-metals in their behavior. Sure. So now if you look at this, and this element graphite is an allotrope of carbon. We'll talk more when we get to carbon. So carbon has tetrahedral structure. So each of the carbon atom can be surrounded by 4 other atoms during chemical bonding. So the same thing applicable to all this. In arsenic, in antimony, and in tellurium, except in boron that can above 5. So this one can above 4, this one can above 4, this one can above 4. So their structure is also interlayer. Like we have in graphite, we also have these layers in antimony, we have in arsenic, we have in tellurium. But the only difference between these is, while in graphite we have planar structure, that we have layers that are planar. Layers are smooth, they can overlay each other. But in this metalloids, they are not layer. They have what is called buckling. So there is something like a corrugated roofing sheet that we see something go up, something goes down. That is structural. That is what we have. But the basic thing we just need to know, the take-home lesson here, is that each of the atoms has tetrahedral structure. 4 other elements can be attached to each of the atoms. So now let's talk more on boron and silicon. Let's start with boron. So in the earth crust, boron does not exist as boron. It exists in company of oxygen, and is very, very minute out of the compounds in the earth crust. It is just the makeup is around 0.001%. That is why you see it's very, very small, the earth crust. So boron is widely distributed in volcanic regions as boric acid. So those are the places where you can find boron. You can find number one is in volcanic regions. So it is present in volcanic regions as boric acid. It's present in dry lake regions as borate, especially in the shale of South California. That is where you can have this borate in excess. You can also have salt of boron or say acid, that is borax. Borax is a very common acid in the laboratory. So elemental boron is chemically inert at room temperature. All we know that is that they don't react at room temperature. So reacting with only 4 fluorine and oxygen to form boron trifluoride. That is if it reacts with fluorine. Then if it reacts with oxygen, we have boric oxide. So at room temperature, they can only react with that. But if you raise the temperature higher, they can react with metals. That is, if you want to drive that reaction by heat, they can react with metal, because there are some reactions that ordinarily they cannot exist, but we can make them to exist if we drive it to them. That is all those endothermic reactions. All non-metals, you can react with non-metals also, except tellurium and noble gases. It oxidizes to this boric oxide when heated with concentrated nitric or sulfuric acid. So when you have reaction with acid, it will not react at room temperature, but if you elevate the temperature small, there's going to be an oxidation of boron to boric oxide. Don't forget, we said nitric acid can also is also an example of an oxidizing agent. We talked about that when we were talking about oxidizing agents. So during the preparation, we said boron does not exist as an elemental state, so it exists as an oxide. So if you want to prepare boron from oxide, the first thing is the reduction. And during the discussion of metals last lecture, we said metals can act as a reducing agent. We have talked about that before. So magnesium is a very strong reducing agent, so we can react magnesium in boric oxide. So if you react then with that, so magnesium is stronger than boron, so magnesium will be able to displace boron and take away the oxygen in heat. So if it does that, there's going to be a mixture of magnesium oxide and boron. So the boron that we have is not pure yet. If you want to make it pure, we are going to react this mixture with hydrochloric acid. If we react with hydrochloric acid, there is going to be a removal of magnesium oxide from that mixture of magnesium oxide and boron. But again, boron will still react with hydrochloric acid to form chloride of boron, because we said boron can react with non-metals. So if it does that, we still need to separate the chlorine from boron. How do we do that? We can heat them. When we heat it, there is going to be a decomposition between boric chloride and what we used to heat it, that is hydrogen at that elevated temperature. So hydrogen will be able to react with chlorine and scatter the bond between boron and chlorine, so it forms pure boron and hydrochloric acid gas. The reaction is endothermic with a lot of heat, that is almost 253.7 kJ of heat involved. So for silicon is much more abundant than boron. In fact, it is almost 1/4 of the total mass of the Earth's crust. Don't forget, during our discussion on metals, we said metals are like 90% of all the elements. And metals do not always, especially the reactive metals, they do not always present in the elemental state. So they present in their compounds. These compounds, the commonest among them is the silicate. So metals are always present in silicate. So that makes silicon to be abundant. That is the first reason. The second reason is there is still a strong reaction between silicon and oxygen. Oxygen is again in the atmosphere, in the earth. So silicon can also react with oxide to form silicon oxide. So all those things contribute to making silicon abundant in the earth crust. So the crust is composed of almost entirely of minerals that are made of silicon compound, as I've explained. So all those minerals constitute the most common rock, soil, and clays in layers and chains like that. In addition, materials such as bricks, ceramics, and glasses contain silicon compounds. So how do we prepare silicon? The same way, the similar way we prepare boron, we can prepare silicon like that. So reduction is the first thing. If you have silicon dioxide, we can reduce it with strong reducing agents like carbon, like magnesium. We can use other elements that can actually reduce this. We can use hydrogen also. So if we do that at elevated temperature, we heat it, there's going to be removal of oxygen from the structure of that silicon oxide. We are using silicon oxide because silicon oxide is very common. But what we have gotten now after this reduction is not pure, because the extremely pure silicon is needed because of the wide range of application to which silicon is being subjected to, especially in telecoms industry, where it is being used to make computer chips and transistors and resistors, even transmitters. So we need silicon in very high pure form. That is why. So we need to purify this from here. So how do we do that? Then we convert this impure into silicon tetrahydride. How do we do that? So we react with hydrogen. After reacting with hydrogen, we are going to have this. Hydrogen will react with this also, but we are less concerned with what is formed here. So if we have silicon hydride here, then we can decompose it the same way we decompose silicon boron trichloride here. So we can decompose silicon hydride. In this case, it's simple. So after decomposing it, we are going to have our silicon in pure form. Let's go to some compounds of boron and silicon. We talk about two major compounds, the halides and the oxides. So for the halide now, boron can react directly with fluorine, with chlorine, bromine, or iodine. In short, elements of the halogen groups. So the fluoride and chloride compounds are always colourless gases. Bromide is a liquid, then iodide is a crystalline solid. So if we look at that, if we look at that trend down the group of the halogen, the fluoride is the smallest, followed by chlorine is bigger, then we have bromine, then we have iodine that is the biggest. So iodine is now forming the white solid, bromine is forming the liquid, the others are gas because of the bond between them. That is what is responsible for that. If you can explain that together with what we have explained under kinetic theory, you should be able to arrive at this. So boron trihalides readily hydrolyze in water to form boric acid. So boron trihalide hydrolyze in water. If you react boron chloride, boron bromide, boron iodide with water, you are going to get boric acid. But boron fluoride do not do like that, because boron is very small, fluorine is very small. So when they react, they are going to have a very strong bond. So the water is not strong enough to scatter the bond between them. So this is the explanation we have talked about in the previous slide. So this is the trichloride of borium reacting with water from boric acid and HCl. But boron fluoride do not react directly with water like that, except with the aid of this, then to form tetraboric acid. But in some cases, we can have silicon tetrahalide forming by direct combination of the element with silicon oxide, and this is what we have. This is silicon tetrachloride, this is silicon tetrafluoride. And note, hydrofluoric acid is the only common acid that will react with silicon dioxide or silicate. Hydrofluoric acid is the only common acid that will react with silicon dioxide or silicate. That is why if you have a glass in the laboratory, they don't store hydrofluoric acid in glass waste, simply because glass is made up of silicon oxide or silicate substance. So hydrofluoric acid now, if you now put hydrofluoric acid in that silicon, in that glass. The bond between fluorine and silicon is stronger than the bond between oxygen and silicon, so the glass will decompose. That is why they don't store hydrofluoric acid in glass. We hope you get my explanation. So silicon hydrides are extremely sensitive to water, except silicon fluoride, and I said it is because of strongness in bond. So the bond is very strong. The strength in the bond of silicon tetrafluoride prevent it from being sensitive to water. So other fluorides that are not strong like that, they are very sensitive to water. So when they react with water, the tetrahedral structure around the silicon, those bonds will be replaced by hydrogen to form silicon hydride. For boron bonds at 700 in oxygen to form boric acid. Then boric acid is necessary for production of heat-resistant borosilicate glass. It is in the laboratory. There are many glasses that are used in the laboratory. So all those glasses, some of them, they are very, very high heat-resistant glasses. All those Pyrex glass, they are made of borosilicate materials and certain optical glasses. So boric oxide dissolves in water to form boric acid. This is the chemistry of the reaction. So silicon oxide, that is silica, occurs in both crystalline and amorphous form, depending on the phase to which silicon is present when it's reacting. So the usual crystalline form of silicon dioxide is quartz. And quartz is very hard. Something that is hard will be very brittle. It is clear because it's crystalline. It is clear. It is colourless since it is clear. So it is useful in many ways. I mean, silicon oxide. It is used in many ways. It is for decorations. It is for precious jewels, on frequency control radios transmit. There are many substances that are made from silicon oxide. No wonder it is abundant in the earth crust like that. So silica takes many crystalline forms and is polyforms in nature. So that is what we have for today. Hope you are able to get the little message we are trying to pass. We don't really have questions on this, but before we go, let us try to have a quick recap of what we have talked about. Silicon and boron are semimetals. They are metalloids, so their properties are in between. They are sandwich in between those of metals and non-metals, and they are not always present. They are not present. They don't exist as elemental boron or silicon. Instead, they have compounds of oxygen. Silicon is very abundant, while boron is scanty in nature. The compounds of boron and silicon are used in the manufacture of laboratory equipment. So compounds of boron and silicon is in manufacture laboratory equipment. I'll give an example of a glassware like Pyrex because of heat resistance. So we need compounds of boron and silicon to do that. But don't forget, we don't store hydrofluoric acid in glasswares, because glass is made of silicon material. Hydrofluoric acid, there is a strong bond between silicon and fluorine and between silicon and oxygen. So if we now have hydrofluoric acid in glassware, the fluoride in the acid will attack the silicon of the glass, and the glass will break. So boron and silicon can react directly with other non-metals. It can react with metals, or it can react with hydrogen. That is all what we have for today. Hope you enjoyed the short lecture. If that is the case, meet us next time on the preparation of non-metal. We are going to spend quite a lot of time on the subject of non-metal, because we need to take some non-metals like hydrogen, like carbon, like phosphorus, like nitrogen, like oxygen. We're going to take them and their compounds in detail before we now come back to metals and their compound. We are going to spend a little while on this inorganic chemistry by the grace of God, God willing, and before we now move to organic chemistry, and then we'll finish the syllabus on chemistry. Thank you for listening. Hope you enjoyed the class. God bless you.